Hello boys and girls. Today I come to you with a more light-hearted insight. Namely, we cover the difference between the representation of the exponential function as a series and with this compound definition where you get the exponential function as the limit of a certain product, right? Because you might know these are two ways of defining the exponential function, and at one point, I was thinking, hey, for finite n, if I don't take the limit, then this is just a polynomial, and for finite n, this is also just a polynomial, right? And so I was wondering, hey, what is actually, like, if I don't take the limit, what is actually the difference between those two definitions before you take the limit? And turned out, just a few minutes and you see exactly what the difference is, and that's what I go through in this video. So the first observation is that we have this formula for the power of a sum, right? So if x and y are some real numbers or complex numbers even, then this is given as this finite sum, where we have this expression with factorials, and then all the combination of powers that we can come up here with this scheme. So there are you sum over k, and so there are m plus 1 of these expressions with some coefficients, and these are also natural numbers, even though they look like rational numbers here. But if you look at this expression and you see that just the different similar factors combined, then this must be some natural number. So we take this formula for granted. And now, if we plug in for y1, so here 1, then 1 to the power of anything will be 1, so this is actually gone. And now we can rescale if we want, right? We can say, instead of considering x, we consider some constant times x, or what we can also do is, since we have this as a running parameter here, we say, hey, let's substitute x with some function of m times x, or times whatever, right? So, and in this case, I will choose as this function 1 over n, so that I write down this expression. I mean, here I substituted the m with the n again, but that's an irrelevant detail. But now I've written down this expression in a way that matches that. And so I can apply this function, because I didn't take the limit. I can just plug everything in, even if this n is now inside. And what happens is that since I have n to the minus 1 here, that with this expression I get here n to like 1 over n to the power of k, and otherwise this is just this formula, right? And here's this k factorial, and here is k to the power of x, so I can actually identify this with this expression, and what I get here is some number that's a function of n and k. I call this a kn, and then this. So I already see here now the difference between this expression and this expression, both dependent on x and n, but not the limit taken yet, is exactly the fact that here the coefficient has some more stuff going on here. And if you take as an axiom that we know that the n to infinity of this and n to infinity of this must be equal, I mean it's both the exponential function as a function that has just one value, then we actually know that the limit of n to infinity of this expression for all k will actually go to 1. So that's something we already know. But we can now take a closer look. So what is this a? Well, let's write 1 over n to the power of k as a product. It's a product over an index j, even though I don't use the j in the expression, and I multiply together these expressions 1 over n. So k times 1 over n is 1 over n to the power of k. And the other thing that's left is n faculty divided by n minus k faculty. And now here you have to think for a minute. Consider, for example, n being 10 and k being 4, right? So that would be the product of all numbers from 1 to 10, and here would be the product of all numbers from 1 to the number 10 minus 4, so the product of all numbers 1 to 6. So this is actually the product of 7, 8, 9, 10, right? What this means is that if I count backwards, like if I consider this to be the product, like this divided by this, it's a product of 10 times 9 times 8 times 7, then I see that I actually can write it down like this. So I start at 10, then I have n minus 1, n minus 2 and so on, and I go all the way back down to n minus k plus 1, so 6 plus 1, right? And that works for all numbers. So this expression, n minus k plus 1, n minus k plus 2, n minus k plus 3 and so on, if I multiply this expression together and I leave the biggest one here, then this is exactly that. And I can write that down as the product over an index k, and you know the index j, and the index j starts at 1. This is the smallest number, and it goes all the way up to k, at which only n is left. So I also have here a product. And this means that this expression is also really just a product, and it's actually similar to the one we looked at in a few videos ago. So we just figured out the coefficient difference here, this factor a, depending on k and n. It's actually just a product over j from 1 to k of this simple rational number. And there you have it. I mean, you can also test it if you take the limit n to infinity of this expression, right, of this polynomial. What really just happens is that all these a's, you know, n goes to infinity, this expression becomes 0, and all these a's become 1, and then you really have just this larger and larger polynomial, and it actually goes to that, right? Okay, so that's actually it for today. I actually have, you know, I am somewhat interested in all things exponential function. You know, I always get back to properties, like I always am interested in all kinds of versions of central limit theorem, and if you view it as a homomorphism between addition and multiplication, and what like almost philosophical consequences this has for theories of probability theory, and how this interplays with entropy and what it means for physical theories. So I have actually a bunch of exponential functions, if you will, or approximation to that, and maybe if there's some interest I will get into that in some other videos. Okay, take care.